Laser color television, or laser color video display utilizes two or more individually modulated optical rays of different colors to produce a combined spot that is scanned and projected across the image plane by a polygon mirror system, or less effectively by optoelectronic means, to produce a color television display. The systems work either by scanning the entire picture a dot at a time and modulating the laser directly at high frequency, much like the electron beams in a cathode ray tube, or by optically spreading and then modulating the laser and scanning a line at a time, the line itself being modulated in much the same way as with digital light processing. The special case of one ray reduces the system to a monochromatic display, as, for example, in black and white television. This principle applies to a display as well as to a projection technique with lasers. History. The laser source for television or video display was originally proposed by Helmut K.V. Losch in the German patent 1,193,844. In December 1977, H.K.V. Losch and F. Schroeter explained laser color television for conventional as well as projection-type systems and gave examples of potential applications. 18 years later, the German-based company Schneider AG presented a functional laser TV prototype at IFA 95 in Berlin, Germany. Due to bankruptcy of Schneider AG, however, the prototype was never developed further to a market-ready product. Proposed in 1966, laser illumination technology remained too costly to be used in commercially viable consumer products. At the Las Vegas Consumer Electronics Show in 2006, Novolux Inc., developer of Nexel semiconductor laser technology, demonstrated their laser illumination source for projection displays and a prototype rear projection laser TV. First reports on the development of a commercial laser TV were published as early as February 16, 2006, with a decision on the large-scale availability of laser televisions expected by early 2008. On January 7, 2008, at an event associated with the Consumer Electronics Show 2008, Mitsubishi Digital Electronics America, a key player in high-performance red laser and large-screen HD TV markets, unveiled their first commercial laser TV, a 65 1080p model. A popular science writer was impressed by the color rendering of a Mitsubishi laser video display at SEI 2008. Some even described it as being too intense to the point of seeming artificial. This laser TV, branded Mitsubishi LaserView TV, went on sale November 16, 2008 for $6,999. But Mitsubishi's entire laser TV project was killed in 2012. LG introduced a front-projected laser TV in 2013 as a consumer product that displays images and videos measuring 100 inches with a full, high-definition resolution of 1920 by 1080 pixels. It can project images onto the screen at a distance of 22 inches. Technology. Lasers may become an ideal replacement for the UHP lamps which are currently in use in projection display devices such as rear projection TV and front projectors. LG claims a lifetime of 25,000 hours for their laser projector, compared to 10,000 hours for a UHP. Current televisions are capable of displaying only 40% of the color gamut that humans can potentially perceive. A laser TV requires lasers in 3 distinct wavelengths: red, green, and blue. While red laser diodes are commercially available, there are no commercially available green laser diodes which can provide the required power at room temperature with an adequate lifetime. Instead, frequency doubling can be used to provide the green wavelengths. Several types of lasers can be used as the frequency doubled sources: fiber lasers, intercavity doubled lasers, external cavity doubled lasers, EVCSLs, and OPSLs. Among the intercavity doubled lasers, VCSELs have shown much promise and potential to be the basis for a mass-produced frequency doubled laser. The blue laser diodes became openly available around 2010. A VCSEL is a vertical cavity, and is composed of two mirrors. On top of one of them is a diode as the active medium. These lasers combine high overall efficiency with good beam quality. The light from the high-power IR laser diodes is converted into visible light by means of extra-cavity wave-guided second harmonic generation. Laser pulses with about 10 kHz repetition rate and various lengths are sent to a digital micro-mirror device where each mirror directs the pulse, either onto screen or into the dump. Because the wavelengths are known, all coatings can be optimized to reduce reflections and therefore speckle. Assembly. Laser signal modulation. The video signal is introduced to the laser beam by an acousto-optic modulator that uses a photorefractive crystal to separate the beam at distinct diffraction angles. The beam must enter the crystal at the specific Bragg angle of that AM crystal. A piezoelectric element transforms the video signal into vibrations in the crystal to create an image. Horizontal and vertical refresh. A rapidly rotating polygonal mirror gives the laser beam the horizontal refresh modulation. It reflects off of a curved mirror onto a galvanometer-mounted mirror which provides the vertical refresh. Another way is to optically spread the beam and modulate each entire line at once, much like in a DLP, reducing the peak power needed in the laser and keeping power consumption constant. Display characteristics maintain full power output for the lifespan of the laser. The picture quality will not degrade. Have a very wide color gamut, which can produce up to 90% of the colors a human eye can perceive by adjusting the wavelength of the laser. Capable of displaying 3D stereoscopic video. Can be projected onto any depth or shape surface while maintaining focus. Applications. There are several realizations of laser projectors. One example being based on the principle of a flying light spot writing the image directly onto a screen. A laser projector of this type consists of three main components. A laser source uses the video signal to provide modulated light composed of the three sharp spectral colors, red, green, and blue, which a flexible, fiber optic waveguide then transports to a relatively small projection head. The projection head deflects the beam according to the pixel clock and emits it onto a screen at an arbitrary distance. Such laser projection techniques are used in handheld projectors, planetariums, and for flight simulators and other virtual reality applications. Due to the special features of laser projectors, such as a high depth of field, it is possible to project images or data onto any kind of projection surface, even non-flat. Typically, the sharpness, color space, and contrast ratio are higher than those of other projection technologies. For example, the on-off contrast of a laser projector is typically 50,000 to 1 and higher, while modern DLP and LCD projectors range from 1,000 to 1 to 40,000 to 1. In comparison to conventional projectors, laser projectors provide a lower luminous flux output. But because of the extremely high contrast, the brightness actually appears to be greater.